Now, I can't remember, do I have a video on homework help for this section or not? I'm trying to remember.
Okay, I honestly don't know yet. I was gonna go and watch those.
Okay.
But I just haven't had the chance to look.
I know I did that with one of the sections, but I can't remember if it was 3.2 or not. But so we are going to, instead of going straight into the assignment that I have for in class, I'm just gonna write down, those of you who are Zooming, I'm just gonna write down your name so that you get credit for attending. And then someone had some questions about the homework, so I'm gonna take some time to go over the homework for section 3.2. So I've got Thomas down, I've got Ansley down, and Hallie. Okay. I've just taken your attendance, so you don't have to worry about doing the in-class assignment since I've recorded you as attending. So let's take a look at the homework. And I'm going to share my screen and go into the homework assignment. This is section 3.2 that we're covering today. So we'll just pick one of the problems. Let's see, how about, oh, I'm sorry. Got to turn that on. There we go. Yeah, okay. So here we have a function h of x equals 2x cubed minus 6x. And these, I think there are only two problems that are kind of lengthy here. Let me see, there's this one. Okay, the first two problems are fairly lengthy, so I'm going to go through this one. You have 5 parts. The first one says to give the coordinates of any critical points and classify each point as a relative maximum or relative minimum. And so I'm going to go ahead and part A, we're going to use the first derivative. Whenever it asks for critical points, you want to set the first derivative equal to 0. Okay, so here's our function. Someone has a question. That's correct, Ansley. You don't have to do the in-class assignment because I'm kind of breaking away from what I had planned and I'm just going over the homework today. So the first part, we need to find critical points. And to do that, you set the first derivative equal to 0. So we have h prime of x using the power rule is 6x squared minus 6. And then you set that equal to 0. We're going to add 6 to both sides. And you get 6x squared equals 6. And we're dividing both sides by 6. And we have x squared equals 1. And then when you take the square root of both sides, remember that's the square root property, you get that x is equal to plus or minus 1. You have 2 values. Whenever you take the square root of x squared, you're going to end up with 2 values. So these are the critical points. So then you take your critical points and you plot them on the x-axis. And so you have -1 and 1. And then you're going to pick test points in each region. And since we're doing the first derivative test, we're going to plug those test points into the first derivative. So let's say in this region, I'm going to pick -2 because that's less than -1. Between -1 and 1, I'm going to pick 0. That's easy to calculate. And greater than 1, I'm going to pick 2. I take these test points and I plug them into the first derivative. So f prime of -2, okay, so here's, if I plug in -2 and square it, I get 4 times 6, that's 24 minus 6 is going to be 18. That's positive. that means my function is increasing because the first derivative is positive. Then in the second region, I pick 0. Plugging 0 into my first derivative, I get -6. So, and I said F, I meant H here. That's an H. So H prime of 0 is -6. That's negative, so it's decreasing. And then finally, I plug in 2 and I get 18. H prime of 2 equals 18. That's positive, so it's increasing. So what you have here is it's increasing, then it's decreasing, and then it's increasing again. So you have a max and a min. And the maximum occurs at -1, and the minimum occurs at 1. So these are the critical points. Those are where the max and min are located. Because you're going up and then down, this is a maximum, and then you go down and then up, that means this is a minimum. So
why would they not just be, why would it not just make like an M shape? Because they're both at 18.
Oh, first of all, when the 18 has to do with the first derivative, and I'm just drawing the function itself. So these numbers are the first derivative. That's the slope. So here's the slope. It's 18, then it's -6, and then it's 18 again. Since these are the first derivative values, those are talking about slope. Remember, the first derivative is the slope of the tangent at the curve. So if you're talking about values, I don't know what that value is. I'd have to take -1 and plug it in here. So that would be 4. So this height here is 4. And then if I plug in 1, I'd get -4. Because I'm using the function itself up here.
Okay.
To get those values. I plug in -1 into the original function. These are the derivatives. Those are the slopes, how steep it is. So when it's positive, it's slanted this way, it's increasing. And when it's negative, it slants this way, then it's decreasing, and then it's increasing again. So the first derivative always talks about the slope. And then this has a maximum value of 4, which occurs at -1, and a minimum value of -4, which occurs at 1. So the function values are found by plugging in your x's, and then the y's are the height. The location is your x. So here it's located at -1. The maximum is 4 located at -1. The minimum is -4 located at 1.
So those random numbers that we've chosen, those are just going to be used for when we have to draw the graph.
They're not really random. You mean these test points?
Yeah.
Those are just picked sort of, I mean, this is any number from this interval. This is any number from this interval, and this is any number from that. You just want to find out what's happening as far as the slope goes. So on this interval, everything is positive. And so I just picked one, and I got that it was positive, so I know it's increasing. Then on this interval, it's decreasing, so the slope is negative, and then the slope is positive again. Okay, so it says there's a relative minimum at 1, -4, and a relative maximum at 1, 4. I think it's -1, -4. That's what I meant to say. There we go. So then part B says, on what intervals is H increasing or decreasing? And so the intervals are, now when you ask where something or on what intervals, you're always talking about x-axis. So looking at our chart here, the region, everything to the left of -1 this way, that's the interval from -infinity to 1. The function is increasing. Then between -1, so -1 to 1, in between those two, it's decreasing. And then here from 1 to infinity, it's increasing again. So these intervals that I'm pointing to right here, those intervals are x-axis intervals. They tell us where something is happening. So it's increasing on -infinity until we get to -1. And then again from 1 to infinity. And the function is decreasing in the middle there from -1 to 1. Then part C says, what are the coordinates of the inflection points? Now, concavity has to do with the second derivative. Concavity tells us, is it opening up or down? So if you look at this picture here of because this is kind of shaped, bending downward like a frown, this is concave down. And then on the right here, it's like a smile, so it's concave up. And at this point right here, this is called an inflection point because the concavity is changing. It's down and then it's up. So right at that point, it's changing. That's called an inflection point. And the inflection point occurs when the second derivative is equal to 0. So the second derivative is 0. So if you want to find the inflection point, you just take the second derivative and set it equal to 0. So h double prime of x, here's h prime of x, that's the first derivative. Now, if we take the derivative of this, 6x squared minus 6, we get 12x. This is the second derivative. And if we set it equal to 0, then x equals 0, because you're going to divide both sides by 12, right? To solve this equation, you're going to divide by 12 on both sides, and you get x equals 0. That is the location of an inflection point. Although you have to be careful, it doesn't possible location. If the concavity doesn't change, then it's not an inflection point. So you have to check to see, but that's the possible location of the inflection point. So let me show you, you have to do your test intervals, just like we did with the first derivative over here. But now the inflection point is at x equals 0. So I'm going to put 0. So I pick a negative number over here, like -1, and then I pick a positive number on this side. I plug it in to the second derivative because we're doing the second derivative test. So the first derivative test over here is testing where is it increasing or decreasing, and that helps you find a maximum min. The second derivative test is testing concavity. So if I take -1 and plug it into my second derivative, right here, 12 times -1 is -12. It's negative, so that means it's concave down. And where is it concave down? To the left of 0. See, 0 is the inflection point. So to the left, it's concave down. So that's on the interval from -infinity to 0. And then on the right of 0, we pick a point like 1, plug it into the second derivative, that's 12, that's positive. So here, the second derivative at 1 is 12. Since it's positive, it's concave up. and that's on the interval from 0 to infinity. So if the second derivative is negative, the function is concave down on that interval. If the second derivative is positive, it's concave up. And so that tells us, now notice, if it's concave down, you have a maximum. And if it's concave up, you have a minimum. So you can use the second derivative to determine if you have a max or min, if you want to go that route. There's several ways of doing these problems. Sometimes you can just analyze it, or you can just use the second derivative. So going back to the problem here, for some reason, it's been really taking a long time to load when I go switch from share screen or going back to share screen. So we'll just have to sit here for a moment.
You just write it like x equals 0, or really write it as negative infinity to 0.
Well, it depends. If you're talking about the inflection point, then you would say it's at 0, 0.
Okay.
And if you want to say where is it concave up, then you got to give an interval.
Okay.
But
it would always be negative infinity to 0, and then 0 to infinity.
Not always. It just for this problem, we got 0 for the inflection point.
Okay. Yeah. So if we had 2 for them, the inflection point would be 2. Then the concave up would be negative infinity to 2, and then 2.
Yeah. If you got your test points that way, yeah.
Okay.
Yeah. I don't know why this is taking so long. Did this to me. It's been doing this to me all day today. So. There it goes. Okay. So when it says, what are the coordinates of the inflection points? Well, we found x equals 0 was the inflection point. And then you got to take that 0, plug it into the original function up here. If I plug in 0, the y value then is also 0. So the origin is an inflection point for this problem. And then the function is concave up on 0 to infinity. And concave down from minus infinity to 0. And then finally it says, which is the correct graph? So here, the inflection point, in this picture, the inflection point is 1, right? Because it's concave up and then it's concave down. So right there, that's not, remember our inflection point for this function is 0. So this graph is out. Going to the next one. Here, the inflection point, it's concave down and then it changes right about here to concave up. This is -1, so that's out. Going to C. Okay, here the inflection point is at 0, 0. It's concave down on the left and concave up on the right. So I think it's C. C is the correct choice because here's the reverse. It's, you'll notice at D, it's concave up on the left and concave down on the right. So this is not it. So C is the correct choice. Okay. So there's one other question like this, but then in the rest of the homework, there are a lot of like problems that you just have to analyze based on concavity. So here, in this particular example, we have a function that has an inflection point at 3, 1. And if you look here, this is the inflection point, but this point that I'm pointing to here, let me make sure that, yeah, I always have to check to make sure I'm sharing it right. Right here is 3, -1 is the inflection point. So this does not have an inflection point at 3, 1. It has it. Okay, looking here, yes, there's an inflection point at 3, 1. It's concave up on the left and then concave down on the right. So
how do you know when it's going to be concave up on the left and concave down on the left?
If it looks like a smile, it's concave up. If it looks like a frown, it's concave down. Let me show
So
you.
it's just how they list them out at the top.
It's how it's bending. So here, from minus infinity until we get to x equal 3, see, we're always focusing on the x-axis. So from far over to the left, all the way till here, it's concave up. See how it bends like a smile?
Yeah, but like, how do we know when to look, like when it should be concave up and when it should be concave down? Like, how did you know that you were looking for concave up on the left and concave down on the right?
I'm just showing you what it is. I'm not looking for it. I'm just saying here on the left, this graph is concave up from minus infinity to 3, and then it's concave down from 3 to infinity. But in the description here, it says, okay, now this is kind of the way they word it here. They want to know, is it concave up at, so we're not talking about an interval here, we're talking about a point. If it says on, then you're talking about an interval. But if it says at, you're talking about a point. So this point, -1, 5, let's find that on our graph here. -1, 5 is right here. Here's -1, and then if you go 1, 2, 3, 4, 5, right there. At that point, here's the question. Is it concave up or concave down at that point? Up, exactly. Because it's kind of bending like a smile. Then, so here, it's concave up at that point. Then they want to know, is it concave down at 7, -3? So I'm going to go to 7, -3. 1, 2, 3, 4, 5, 6, 7, -3. It's concave down. So this graph matches their description. So B is the correct choice. It has an inflection point at 3, 1. It's concave up at -1, 5, and then it's concave down at 7, -3. So this one is the correct choice. This one is close, but the inflection point is right 3, -1. And so this one fails. And then here, it's concave down on the left and concave up on the right. So B is obviously the correct choice. Okay. Here we have, for the graph shown, identify the points of inflection and the intervals where the function is concave up or concave down. So looking at this graph, on the left, from minus infinity until we get right here, it changes, right? So to the left of 3, minus infinity to 3, it's concave up. And then from 3 to infinity, that's on the right, it's concave down. So the inflection point is right here at 3, 1. So the inflection point is 3, 1. Then the function is concave up on minus infinity to 3. And it's concave down on 3 to infinity. Okay. Now it says sketch a graph that possesses the characteristics listed below. So F is increasing and concave up on minus infinity to 1. And then it's increasing and concave down on 1 to infinity. So it's everywhere increasing, okay? So B is out because look, it's going down as you move from left to right. So this is out, that's decreasing. This one is out because it's also going down as you move from left to right. So it's either A or D. Now, A has an inflection point at 1. So here's 1. But on the left, it's concave down. And on the right, it's concave up. And this one is on the left concave up and on the right concave down. So this is the correct choice. See how these are just reversed. They're both increasing everywhere, but this one goes down and then up, whereas this one goes up and then down. So D is the correct choice. Does that make sense? Okay. You're what?
I just said award.
I know it looks bad, but the way you do these is by the process of elimination. Okay. So let's start with the first one. The first derivative evaluated at -1 is 0. We're talking about the first derivative. That means -1 is a critical point. So you have either a max or a min at -1, right? So looking here, -1, nope, there's no max or min. That one's A is out. B, -1, there's a minimum value. So yes, right here, the tangent is horizontal. So the first derivative at -1 is 0. So now you stick with this graph. Don't give up on this graph yet. Go to the next criterion.
The next one was a 0.
Well, the second derivative at -1 is less than 0. That means it's concave down at -1. What does this graph look like? Up at -1. So I have to eliminate this graph. So now we go on to the next graph. Okay. This one has, yes, it has a critical value at -1. There's a maximum. And notice at the second derivative, it's concave down. So the second derivative is negative. So therefore, C is still in the running. Now we got to go to the next criterion. If you evaluate the function at -1, it's equal to 6. Yes. At -1, the value of the function is 6. Let me see right here. And it says the first derivative at -5 is 0. So let's take a look at that.
And concave.
At -5, 1, 2, 3, 4, 5. Yes, there's a minimum, relative minimum there. So that is going to be, the first derivative is going to be 0 at this point. It looks like C is the choice. Let me see if I can go to D and eliminate. D at -1, there is no, the first derivative is not equal to 0 at -1, right? It has to be a max or min. So that one's out. So C is obviously the choice there. So you do it by elimination. You go down the list until I didn't even check all this stuff over here. I can just already know that that's. This one is very tricky. This problem, math department put this one in here. The question is the blue one the derivative of the red one, or is the red one the derivative of the blue one? Okay, that's the question. So let me make sure I got that right. Okay, so what you'll notice is the blue one is 0. That means the red one, notice it has a maximum there. It's a flat, it's a tangent, horizontal tangent. And then right here at 0, there's a horizontal tangent, and the blue is the 0, is equal to 0 when this has a horizontal tangent. Here, the blue one is 0, and there's another horizontal. So the blue one is the derivative, and the red one is the original function.
How did you just get that?
All right. Those of you who's Zooming can't really, I'm walking over to the screen here, so you can't see that right now. Okay. At the point where this blue one is 0, that means the derivative is 0. The red has a horizontal tangent. And here, this has the value of the function is 0, and the red one has a horizontal tangent. And then here, the value of the derivative is 0, and the horizontal tangent right there. So the blue one is 0 when the red one has a tangent that's horizontal. Okay. So that's how you can tell. Look here, if the red one were the derivative right here, red one is 0, there's no horizontal tangent for the blue one. So I know that this red one can't be the derivative of the blue one. It's the other way around. The blue one is the derivative.
And so the red one is the original.
Right. So it says here, oh gosh, I'll just assume, I'll let you answer that question. Don't want to take the time to do that, but that's how it, the red one is the function and the blue one is the derivative. Okay, this one says use calculus to prove that the relative minimum or maximum for any function f as shown below occurs at x equals minus b over 2a. So we have that's the vertex formula, right? And so this is a parabola, and it could either open up or it could open down. In this particular example, it doesn't, we don't know what A is, but it doesn't matter. This value is x equal minus b over 2a. That's where the vertex occurs when x is minus b over 2a. And you can see at that maximum, there's a horizontal tangent. And at the minimum, there's a horizontal tangent. So the derivative is going to be equal to 0 at those 2 points. So, oh, I'm sorry, my bad. Sorry about that. Hold on, let's go back. All right, here we go. So we have a function ax squared plus bx plus c. And that's our function f of x. It's quadratic. So it's a parabola. It either opens down or it opens up. And by that vertex formula, the location of the maximum or minimum is at x equal minus b over 2a. And if you take the derivative of this function, using the power rule, 2 times a, subtracting 1 from the exponent, you just get x. And this is the linear part, so the derivative is the slope, which is this constant in front of the x. So here's the derivative. If I set that equal to 0, then I can find the critical values, which is where the max and min occur. And so solving for x, I subtract b from both sides, and then I get 2ax equals minus b, and then I divide by 2a. And so, of course, x then equals minus b over 2a. So this is the critical value for a parabola or quadratic function, okay?
So if we can solve it like that, it's a critical value, but if we can't solve it like that, it's the inflection point.
Well, this is a special case for quadratic functions because all quadratic functions can be written in this form. And so for all quadratic functions, the critical point is minus b over 2a, and that's exactly where your max or your min occurs, okay? I'm not sure if I answered your question. What was your question?
So if we take the derivative, like say it wasn't this one, it was just random numbers, but if we take the derivative of that and it gives me the answer that matches up with the one that was in the question,
then you've done it. Exactly. Exactly.
Okay.
So if you go back here, where will the relative minimum or maximum for the function occur? And it's a critical value because we're doing the first derivative.
So if that didn't match up, that would be inflection point.
If the second derivative, if you're doing the second derivative, then it would be an inflection point. I don't know why they do it this way. Basically, when they say prove something, I just proved it right here. So they can't really, you can't really put that into the system. So I don't know why they set up this way, but. Okay, so what's the difference between a critical value and an inflection point? A critical value is when the first derivative is equal to 0. An inflection point is when the second derivative is equal to 0.
Okay.
then they want you to determine what is the first derivative, and we did that. 2ax plus b was the first derivative. And then x equals minus b over 2a. When you set it equal to 0 and solve it, you get x equals minus b over 2a. And the second derivative is going to be, so if you take the derivative twice, it's going to be 2a. Right? Here's the first derivative, and if you take the derivative of that, then it's going to be 2a. Okay, so that's that one. I don't really want to try it again. Why do I have to try it again? Did I get it wrong or something? No.
Yeah.
That's weird. Okay. Okay. This particular problem, it says we have a graph, and it says at x equal -3. I'm wondering if those of you who are Zooming, just a minute, I have a, can you see my cursor? Does that show up when I'm pointing to things?
Yes, we can see
Okay,
the cursor.
good. I figured you did. I just couldn't remember. So I'm pointing to this value here at x equal -3. And it says the graph of f is decreasing at that point. It decreases, right? It's going down as you go from left to right. And it's concave up, or no, concave down, because it's bending down like a frown kind of. So that's how you do those problems. You're just looking at the graph. Now this one has been tricky for a lot of students. So let me just, which of these is the largest? Well, notice you're evaluating three different things. -3 at the second derivative, the function value, and the first derivative. And you're comparing those values to see which one is the largest. The second derivative is negative, right? Because it's concave down. Right here at this point, it's concave down. So the second derivative is negative. The function value is equal to 0 because it's on the x-axis. And the first derivative at -3 is negative. So really, that's not helping me. And oh yeah, which is the largest? So 0 is the largest. You've got two negative numbers, and then you've got 0. So 0 is the largest. So it's kind of a tricky problem. They just trying to ask, you know.
Is it always going to be the one with no derivative?
Not necessarily. It just depends on if they say the smallest or if they say the largest.
So which one would be the smallest in this?
There is no smallest. It cannot be determined because in this particular example, these two, A and C, are both negative, so you can't determine which is the smallest. But since 0 is greater than both negative numbers, then you know that's the largest. Okay. Here we have a function. The first, so the function that is listed there is positive. Why is it positive? Because it's above the x-axis, right? That this blue line is above the x-axis, so it's positive. So the function is greater than 0. The first derivative is positive because notice it's increasing as we go from left to right. So
how do you know where the first derivative and the second derivative and all that is?
All right, the first derivative is whether it's if its first derivative is positive, it's increasing. If the first derivative is negative, it's decreasing. Because the first derivative is the slope of the curve. And what is the slope of this line? It's positive.
Okay.
Because it's slanted this way. And you're increasing. Now, because it's a line, the first derivative is a constant. I know this is terrible.
I think I'm in the wrong math.
What? I know it's funny. Because it's a line, I know, I totally get you. Anyway.
Laughing.
I'm sorry, we're just having a moment here where we're just laughing. It's just, you couldn't see the look on her face. I could see the look on her face, so it was just funny. Okay, so because it's a line, it has a constant slope, therefore the derivative is constant. So if you take the second derivative, what is the second derivative? If the derivative is constant and you take the derivative, 0. Because the derivative of a constant is 0. So this one is equal to 0. This one is greater than 0. There we go. Did you have a question? Someone on Zoom have a question? I can hear somebody talking. But... All right. That's why we're going through this homework with you. Okay. The graph of a company's profit, P of T in dollars, is given here. So here's the graph. Estimate the nearest whole numbers labeled on the horizontal axis with any values of T where the second derivative is 0. Okay, what does it mean for the second derivative to be 0? No, it's 0.
The inflection point.
Exactly. So we got to find all the inflection points. So here we can see it's concave up and then it goes concave down. So right there is a inflection point. So 8, x equal 8 is the location of a, or t, I'm sorry, not x, t is 8. Okay. Then going back to the graph, let's see here. Concave down and then concave up. So it looks like right about here, it's changing from this side is a frown and this side is a smile. So right about there at 16. So I'm going to put 16 there in my list as well. And then finally, here it's concave up and then it goes concave down. So at 28, right there is another inflection point. So I'm going to put that in my list. Okay. Now, part B says list any values of t where the second derivative is the same as the first derivative. All right. That would be where they're both 0, right? We can't look at it and tell if it's like the numbers are the same. It would have to be the zeros. So here it's decreasing. So the first derivative is negative and then the first derivative is 0. And remember 8 was also an inflection point. So the second derivative is 0. So this is both an inflection point and a critical point because you've got a horizontal tangent there. So that was 8. And I think that's the only spot because here the first derivative is 0, but that's not an inflection point. And then here the second derivative is 0, but that's not an inflection point. So I think 8 is the only one. And here it says the first derivative is greater than 0 and the second derivative is equal to 0. That means it's an increasing the function is increasing and it's an inflection point. So if we look at our graph, here's an inflection point and the function is increasing. Not at that point, the derivative is 0 at that point, but right here is 24 was an inflection point, and notice that it's slanting in the positive direction. That means it's increasing right there. So 24 is the answer to this one. And here's an inflection point, but it's decreasing because it's slanted the other way. So 24 is the correct answer there. Now we want the first derivative is negative. That means it's decreasing and the inflection point. And that was right here. Here's the inflection point. It changes concavity and it's decreasing at that point. So that would be 42. Notice how when I answer this question, I'm looking at the x-axis. You always answer the where with the x value. So 42 is the x value. So I plug that in. Okay, and then here we have the first derivative is 0 and the second derivative is positive. That means if the second derivative is positive, that means it's concave up, and the first derivative equaling 0 means it's a minimum value. It's a relative. So here, right here, it's concave up, and that's a relative minimum at 48. So these types of questions really test your understanding of first and second derivative.
Why couldn't it be one of the first ones then? Like right at between 17 and between 12 and 18.
All right, between 12 and 18, let's look. So it's concave up because it's bending up, and the first derivative is positive at this point because it's increasing there. Is that what you? So we're looking for when the first derivative is 0. That means it has to have a horizontal tangent.
It was kind of past that for anxiety for like the first time.
I don't think this person's talking to me.
You know, we're in pet days. That's not.
Let me just mute them. Hold on.
There's just a lot of anxiety, and then getting active like that just picked me off. Then I just wanted to hold my baby, and it just we walked out. I mean, if I was going to tell Tommy all that, I probably would have heard.
Oh, there it is, right there. I think I muted her. Okay. It looks like she's muted now. Oh, right here.
Yeah.
Okay, there we go. Okay, going back to this now. We only have 3 more minutes left, but the last part. Now the first derivative is 0. That means you've got a horizontal tangent. And the second derivative is negative. That means it's concave down. So if you look here, here we have a horizontal tangent and it's concave down. And you go to the x-axis, that's 36. Does that make sense? So just basically it boils down to this. The first derivative is all about, is it increasing or decreasing? And if it's 0, it has a max or min, the horizontal tangent. Second derivative tells you if it's concave up or concave down and where the inflection point is.
So then what about C and D? It does not have a horizontal tangent, and so C, horizontal tangent and concave up.
Yeah, exactly. And D, horizontal tangent, but concave down. And you always look at the x-axis to get your answer, where something is happening. You just draw a vertical line down to the x-axis and that'll tell you where the location is. Okay, so I hope that helped. Oh, we didn't finish it. There's part E. Concave or inflection point and horizontal tangent, that would be right here at 12. Inflection point and horizontal tangent. So that's 12. I think if you go through this problem real carefully, when you do the homework, it'll start to make more sense when you do it on your own, you know, and have to really think about it. It's hard when I'm just up here saying it so fast and you're trying to follow what I'm saying, and then I'm on to the next thing, you know. So that's one nice thing about the videos. You can go back and revisit it. So this video will be available in, do you guys use the cloud recordings very much? When you,
I mostly just do the lecture video.
Right. Yeah. So, but if you get stuck on the homework, you can go back to this cloud recording and see how we did that. We didn't get quite to the end. We still have one problem left, but I think you can figure it out.
That
okay.
Help, a lot.
Any questions for anybody Zooming? Like I said, you can use the cloud recording if you want to revisit this, because I did just about every homework problem on here from section 3.2. So, and those are due tonight, tomorrow night. Okay, got it. So you should be good to go.
Thank you.
Yeah, have a good one. Sure.